If you clicked on this video, you're probably interested in ELF files, and in this video I'm going to show you how you can write your own by just adding bytes to a file. Before we look at the actual format, let's think about what we would expect to be in such a format, in such a file. So let's imagine that we are the operating system and we need to load a program into memory. What do we need to know about that program? Obviously, we need the instructions encoded in hex. So for example, if we want to move a number into a register, that would be here the B8, and that would move a number into register. So we have a bunch of these machine instructions encoded in hex values. Okay, so that's the program itself. We obviously need that. What else do we need? We need to know where in memory we would need to map these instructions, because some instructions might include absolute values. So if we have an instruction that says jump to location 2000, we need to ensure that at that location 2000, there is the thing that we're actually looking for. So the right thing is being loaded into memory at the right location. And finally, we probably also want to know where our program starts. So what is the first instruction? Okay, let's start by looking at the ELF file format. And we can see that it's the primary executable format used in Unix system. And if we scroll down, we see it's not only used in Unix, but also for things like PlayStations or even to some extent the Android system. If we scroll back up, we can get an idea of the structure of the file format. So if we look in here, we see all the bytes of the file, and we see that it's roughly separated into three different parts. The first part is the header part that includes all the meta information about this file. What kind of segments need to be loaded into memory? Where in memory do you need to load them? So all the information we just talked about, and some things that make it easier to read the file, like offsets, how long things are, what kind of architecture this was written for. Then we have the program itself. They call it sections here. I don't know if I like the name, but this includes the instructions and maybe some data where we also need to load along with our program. For example, some strings that we want to print out. And finally, we have what they call header 2 out of 2. This is basically documentation. It's not necessary to run the program, but it helps us if we want to disassemble the program or look at the program later at this binary code and make it more readable through this assembly process. So this will store information about the program, how things were named in the assembly code, how jump locations were named, how sections were named. It's basically just documentation that makes the stuff disassemblable and readable afterwards. We'll start off by creating a binary file with a traditional assembler to have a look at the structure and what it looks like. And to this end, I've just provided a very simple Hello World program where we load Hello World into memory as a buffer. And then we simply do a system call and say, hey, anything at this location, print that to standard out. And we can assemble that into a file like this and execute it, and of course it prints Hello World, but more importantly, it of course creates the actual binary file where we want to look at. Now if we look at the binary file, the first thing we notice is that it starts by saying ELF. And these are what they call magic number. Basically a convention that if anyone reads this file and the first 4 bytes are these values, we know, okay, this is an ELF file, and therefore we can expect a certain structure afterwards. Now, what that structure looks like, we can go back to Wikipedia and have a look at that. This is the file header, and we can see that the first 4 bytes that we just looked at are this magic number. And then we say, hey, is this a 64 or 32-bit file? Is this in little or big Indian, and so on and so forth. So this details the exact structure we expect. So let's have a look at the structure of our file here. For this, we're going to use a utility function with the flag H for header. This will print out all the information stored in that header. So we already saw that it is for 64-bit, it's little endian, it's for Unix system, and it's an executable. So let's just verify that we can see these values here in our structure. So let's pick maybe the 2 and the 3, what do they mean? So we see, okay, this is a 16 offset. Let's go back to Wikipedia and go through these, and 16 offset will be here. We can just count these. This will be 8, 9, and then another 7. And then we go in here and we see, okay, this is an executable because we found the number 2. One more interesting thing about this buffer here, let's call these 7 bytes, that are just reserved for the future. If the ELF format will ever be updated, they can use these 7 bytes to make further specifications, but for now they'll just always be 0. So if we go back to our file, we see that, okay, we specified this, we look this up, then we have a bunch of zeros, then we say that this is, what was this? That this is an executable, and next we will say that this is a AMD x64, so F3E, that's the value we find here, right? Okay, whatever values do we have here? We have an entry point into our memory. So this says the first instruction you have to execute, you'll find at this location. Now we haven't loaded anything yet into memory. That's what we're going to look at next. What's responsible for loading stuff into memory are these program headers. And it says that the first program header will be 64 bytes into the file. So we know that this entire part here, that's encodes all the information we see in this header. And then next we'll find a program header, and we know that there are 56 bytes because it's also specified here. Now we can look at other program headers with the -L flag and on the same utility. And this will tell us what parts need to be loaded into memory and at what location do they need to be loaded at. So we see the first part goes from 0 to with an offset of A8. So, we're loading from 0 to A8, we go all the way down A8. So this part we're loading into memory. We want it to be readable, and yeah, that's basically it. And then reloading the next part into memory, we can see that the assembler just added a bunch of zeros to make it align to the next 1000 in hex. So these zeros are all unnecessary, they just happen to be added by the assembler. Now if we jump to 1000 here, that's the next section that gets loaded into memory. We see at 1000, please load with an offset of 1F, so we go down 1 and then F over. So this part needs to be loaded. It needs to be loaded as readable and executable, and it needs to be loaded at this memory address. This is actually the program code we've written here. We could go and look up that move is actually B8, and that the next move into a different register is BB and so on, or we can just do an object dump, which actually disassembles the file we're looking at here and gives us this information. So we can see that, this B8, 4 and so on is moving the immediate value of 4 into the EAX register. That's exactly what we have here, and that's what we also find in our. So let's look at the last program header, which is this one. And this says, hey, there's something at location 2000, and please load that into this memory location as readable and writable. And this will be our hello world string that we want to print out. That is here our data section. So if you scroll down to 2000, that's exactly what we find. As we have seen in the beginning, that's basically all we need to run an executable. We know what to load in memory. We know what the first instruction is. That was here. The first instruction is here. We have loaded our instructions into memory, and we've loaded the data into memory. So that's basically all we need to run the file. In order to disassemble these things and get nice output like we got in here, how would we know that this is called start? How would we know that how the sections are called? And this is where the documentation part comes in. So let's read again the entire ELF file with A, and we can see that we have different section headers. Now, these section headers, as I said, are basically documentation about how we name things in our file, how we name certain symbols, and so on and so forth. One perhaps oddity is that these names are not directly encoded into these structures, into these section headers, but they're stored separately. Why is that? Because that allows us to make these section headers the same size. So all of them will be 64 byte. So, this will be a section header, this will be a section header, and so on. So that's 64, 1, 2, 3, 4. Here, that's until here. And if we had to encode text and symtab and section header string table into here, they would be different sizes. They wouldn't all be the same size, which would make it more difficult to work with. And therefore, instead of having the text directly in here, they're setting an offset, and they're setting an offset because this is a section header into the section header string table. So we see we have a 1B, which is the offset. If we look into Wikipedia, we can see that in fact it's a section header. The first 4 bytes specify the offset into the section header string table. So the section header string table we'll find in the file at 20df. We go to 20df, so for the entire thing. So the section header string table starts here, and then our section said, hey, I have a 1B offset, so 1 down, B over, and we land exactly at the dot text. Yeah, dot text. And The utility basically does that for us, but in the file, that's how it is encoded. Now we have a basic overview of what the thing looks like. We will start by redoing this ourselves without assembler by just writing the bytes ourselves into a program. So our goal is to do the exact same thing, but perhaps a bit simpler. So we saw that we have 3 different program headers that specify different parts that we want to load into memory. It's done properly here, we're loading the headers and the program headers into memory as only readable because we don't need to execute them, we don't need to write into them. Similarly, it's loading the data as readable and writable and not as executable. We're not going to do this, we're going to make it very simple, we're going to load everything into memory at once. One thing that's perhaps important to note is that we actually do need to load the ELF header and the program header into memory. Initially I thought, like, why would we be loading that into memory? I just want my instructions in there, I just want to run my program. But it turns out that we actually do need to put the ELF header and the program header into memory for Linux to be happy, so they can look up these values during runtime. So we do have to load them. Let's start by just writing our ELF header. So, we just open a file and we are ready to write into that. We know that the ELF header is 64 bytes, so let's start by making a byte array. And next we need to set the first 4 values to the magic number. And I just copied that over. This will be the only part that we have to put in as a big endian. The rest will all be little endian. So now let's just write it into the file and have a look at what that looks like. So go run, we get a new file. Let's move that to the right. And we see, we have our magic numbers, our 4 bytes, and the rest is obviously 0, but we get the entire 64 bytes in our file. So now we have to go back into Wikipedia and look up the exact structure that we need to adhere to make a valid ELF file. So the next byte will tell us if it's 32 or 64 bit. So we have to set that to 2. And then we have to say if the file is encoded little or big endian. So we have to set this to, little endian is 1. And we set the ELF version. And then we have to skip a few of them. These are reserved for future changes. We're going to skip them. We just leave them at 0. And then at 16, we're gonna add that we want to make an executable. So we just go through this and I will make the entire structure and skip that part for you. Okay, cool. Now we have the entire header specified. We know it's an executable, we know on what platform we want to run. We don't know the entry point yet, so I just set that to 0 because we don't know where the instructions will be in our file yet. But we do know that the program headers will be right after our ELF header. So the next byte in our file will be the program header that we'll specify next. And we also know that the program headers will be 56 bytes long. Now if we just run that again, we can see, okay, all these values get filled out. And we'll go ahead and do the same thing for the program header. We go in here and see, okay, we're doing a 64-bit file. The first 4 bytes need to specify what we want to load in memory, so we set them to 1. The next 4 need to specify that is executable and writable, and so on and so forth. Okay, cool. Now we have our program header. We say we want to load this stuff. This will be readable and executable. We're starting from the beginning of the file, so from 0, and we want to load all the way to the end, but we don't know what the end is yet. We haven't added our instructions yet. We haven't added our data yet. So this is something we need to add later on once we know the length. The virtual address here, that's something we can make up. It doesn't really matter. We just need to be consistent in our program. And there are a few limitations. It cannot be 0, it cannot be too high. So I just copied basically the same value that was proposed by the assembled version of our Hello World program where we looked at before. Speaking of which, we already assembled this one, right? And we basically want to do the same thing. So we could go in and look up, okay, what is the encoding for moving a value into this register? We can look at these instructions and how they are encoded, and then copy them over into our program. And this will be the instructions we also want to run. And the only exception will be that this program expects the hello string at this offset, and this will obviously be different for us. Okay, as you can see, I just literally took all of these values, put them in a byte array, and then we also write that. And finally, we need to add our hello world string so that it will be loaded into memory so that we can print it out. Okay, That's basically it. We can run this and we get a file. And now we have all the informations we need to fill out the blank spaces we left in before. We said in the program header, we're saying what parts of the file we want to load. We want to load the entire file. We now know how long that file is, from 0 to A4, here A4. So we can put that in here, XA4, and the same for the memory size. It will occupy the same size. And then we also need to say where the first instruction of our program will be. We also left that blank in the actual header itself. So we know the first instruction is here, this B4000. So we're looking at 78, right? So we take this value and we add 78 to it, and that will be the entry point in our program. So remove 2, 7, 8, and that should be the entry point. And finally, remember we simply copied this from here, and this value where the hello world string is stored is obviously wrong, because it will now be loaded at 4000 plus, let's go over here, 97. So we know that the hello world string is at 400,097. So we just need to change that in here. So we don't have this 2000 offset, and here we will have 97. So yeah, that should be basically the program. So let's see if it works. Okay, permission denied. Let's make it executable, run the same thing again. And yes, we actually get hello world. Wonderful. So we have an absolute minimal version of this hello world program. We see it is much shorter than the original that we tried to copy. And that is because we skipped a few things. We only have one program header. And as you can see, most of this file is just a 0 buffer. But we also skip things that are kind of important. So if we run the same commands that we used to inspect the original file on our program, we find that it is indeed able to read the header itself. It is able to read the one program header that we have, but it's complaining and saying, hey, why aren't there any section headers? And same is true if we try to disassemble this. So if we try to disassemble this, it's going to say, hey, this is a weird file. I don't know what to do with this. So in order to make this readable for normal utilities, we need to include the section headers so that it knows where to find the instructions, where to find the data, and so on. Now, in order to do this, we use the same approach. We go to Wikipedia, we go to the section headers, and we build the byte array the same way. We see, okay, the first 4 bytes are this offset into the string header table. The next 4 bytes are this, the next 4 bytes are 8 bytes are that. And we build up the section headers. And as we have seen, it gets a little bit complicated with these offsets into this table. So the approach that worked best for me is not building the file completely by myself, but completely trying to copy the assembled file that the assembler assembled for us with all these 0 buffers and so on. And that way I can make some changes to my own file and run a diff command and see what is wrong. And I've already done that for you. Then run a diff, minimal elf, and we want to compare that to this min. We see that it's almost completely identical. The only part I was too lazy to include are here the sim tabs, where we define the symbols in our program. But we have the section headers, and this is indeed enough to actually get an object dump out of this file. As we can see, we get an object dump, we can read our instructions, and if we run the read elf all, we can see that we can now read our section headers. The only thing it's still complaining, obviously, about the symbol table, because I didn't copy it. It's just left empty. Okay, I think I'll end it here. I'll provide both the minimal version that we created together and my almost valid ELF file once I clean it up a bit. And I think it's kind of a nice exercise to go from this minimal version to an almost valid ELF file. Bit tedious, but also fun. And I hope you enjoyed watching this.